Oh, yay! Here we come to our final video in this lesson of these really rad manipulations of integrals. And in this one, I'm going to show you a couple of ways that we can manipulate integrands involving trigonometry and how we can use their identities to get ourselves into better shape for integrating. Let's check these out. So in this first one, you've got 1 minus cosine theta over sine theta. Now, this kind of problem right here, what I prefer to do is I like to multiply by the conjugate top and bottom. It's not the only way to do it. You could actually split into fractions and do 1 over sine theta minus cosine over sine theta and rock and roll from there. But again, I prefer to multiply top and bottom by 1 plus cosine theta because, you're going to see in a second, that brings into play a very neat identity. Again, these are some wacky manipulations, but when you learn them, you start to see different ways of how you could manipulate other integrals. That's the purpose of all this. Is to get better at saying, oh, I see. I didn't realize I could manipulate things like that, but now I can. Very cool. So we've got that. I multiply by 1 plus cosine theta top and bottom. That's going to bring into play something very neat on the top. You're going to end up, when you FOIL this out, with 1 minus cosine squared theta. And that's all over, and I'm going to keep that factored, sine theta times 1 plus cosine theta. Very nice. Okay, so what does that do for us? Well, don't go now and factor this thing out. There's another way that we can keep simplifying this. Recall the identity, very important one, the Pythagorean identity. We're going to use that twice in this lesson. Sine squared plus cosine squared theta equals 1. Super important. So that also means that 1 minus cosine squared is sine squared. So this is sine squared. So you get the integral of sine squared theta. Oh, it's beautiful. So you always wondered why you learned those identities. One of the reasons was so you can manipulate trigonometric integrals. How about that? Anyway, you get sine squared over sine. So one of these sines is going to divide out. So all of that manipulation, keeping in mind we've done no calculus yet, and we get sine theta over 1 plus cosine theta. Now, the reason why we like this is we now can take the derivative of that will give us some form of sine, whereas the derivative of this would give us some form of cosine, but it wouldn't give us the 1 that we needed. So if I let u equal to 1 plus cosine theta, du is going to be equal to the derivative of that d theta, which is minus sine theta d theta. Oh, there's a sine theta d theta, all right. So we're going to put a minus sign there so it's equal, and of course multiply by a minus 1. And that gives us minus the integral of du over u. What? Typical old ln. So that's going to be minus the ln of the absolute value of u plus c, which simplifies to minus the ln of the absolute value of u, 1 plus cosine theta. When you when you differentiate this to check your answer, you're going to end up back, well, here, sine theta over 1 plus cosine theta. If you multiplied that top and bottom by 1 minus cosine theta, you could actually end up back here. So they are equivalent. A very neat manipulation. All right, if that didn't whet your trigonometric appetite, I don't know what will. Let's do this one. So tangent squared comes up, not too infrequently. I've seen this on some tests. That 5's there just to distract you. So pull that 5 out. You have tangent squared 3x. Now, if you haven't memorized the identity I'm about to show you, we're going to manipulate this to get tangent squared. So I'm going to start out with sine squared of theta plus cosine squared theta equals 1. Tangent squared theta involves secant squared and a 1. Where do we get that from? To make a tangent squared theta, we can divide every single bit here by cosine squared of theta. And if we do that, we're going to end up with some beautiful new expressions. But you got to divide everything by cosine squared. That gives you the tangent squared that we want. And you don't need to know to do this. I'm just showing you why what we're about to do makes sense. Equals secant squared theta. And that's because 1 over cosine squared is secant squared. And lo and behold, we get the identity, which if you didn't memorize is right here. Secant squared theta minus 1. So it's this identity that we're going to use. You could memorize it too, but I want to show you where it came from, how it related to this. So tangent squared is secant squared theta minus 1. Why do we like that? More on that in a very short while. Tangent squared theta is 3x, so you're going to get secant squared of 3x. Theta is 3x, remember, that's all that is, minus 1. So why do we like that? We like that because the integral of secant squared is tangent. right? It's got a nice integral. So we've got 5, and I'm going to do a little bit of manipulation here. Tangent of 3x, because the derivative of tangent is secant squared. 3x, normally a 3 would get multiplied out with the chain rule when you take a derivative. So we've got to divide by 3. Some of you might use u substitution and let u equal 3x here, and that's fine too. But again, the derivative of tangent 3x is secant squared 3x times 3. There is no times 3 here, so we got to divide 3 to mitigate or balance out that 3 that would come out. Minus, keep in mind that 5 goes with this 1, 5 times x, because the integral of 1 is just x times the 5 plus c. Ah, what a cool manipulation. That's just a couple of trig identities. I got a few more of those in the exercises for you. Can't wait to show you those. But until then, great job. Peace.